Example 3 asks us to find the absolute max and min values of x to the 2/3. And if you know anything about Mrs. Meyer, this is my favorite function. This is the kindergarten seagull or your first grader seagull graph, your caca. So x to the 2/3 looks like this. It has a nice little cusp at 0. And then notice they give us a closed interval of -2 to 3. So we're looking from -2 out to 3. We're only looking from here to here. So I can already identify by looking at this picture where my max and min are going to happen. I've got my minimum value right here, and plugging in 3 is going to give me a bigger number than 2. So I can identify that's where my max is going to be. It's good to have a picture in your head of where these are going to be, and then now let's do the math to support our answer. So to find maxes and mins, we need to identify if there are any critical points. And to do that, I have to check 2 things. First, I need to know if the derivative does not exist. And I know this graph, so I recognize there is a cusp at x equals 0. So that's going to be considered one of our critical points. The second thing I need to check is where is the derivative equal to 0. So let's do the derivative of x to the 2/3. We get 2/3 x to the -1/3. And we want to set this equal to 0. Now, that's the same thing as saying 2 over x to the 3x to the 1/3. So if I were to multiply by this bottom, I get an answer of 2 equals 0. And that never happens. So there is no place where the derivative is equal to 0. So we just kind of say, yep, there's no critical points from the derivative equaling 0. But we do have this critical point up here to consider. When you find a critical point, what we need to do is check that critical point. It's not a guarantee that it's a max or a min just because it's a critical point. We have to do something called a sign chart. I'll write it out, sign chart, not S-I-N-E. So we found that there's a critical point at x equals 0. The other thing I need to consider is I have endpoints, -2 and +3. I got this value from the derivative, so I'm going to label this f prime of x. I want to plug in values between -2 and 0. I would pick -1. And you plug it into the derivative. If I plug in -1 to the derivative, I get a cube root of a -1, which is negative. So I get a positive divided by a negative, which is a negative. Then I have to plug in a positive number between 0 and 3. So if I plug in a positive number, I don't even care what the number is. What I recognize is I'm going to get a positive over a positive, which is a positive. So because it changed signs and it went from negative to positive, it went from decreasing to increasing, that results in a minimum. Now there's no other places where it's changing signs to get my maximum. The last step that I need to consider is I have to check my endpoints. So step 3 is check your endpoints. So I want to check the ordered pair at -2, and I also want to check the ordered pair at +3. Since we're talking ordered pairs, we use the original function. So I get -2 to the 2/3, and I get 3 to the 2/3. Now, if you put those on your calculator, you can, go ahead. But if I square this and then take the cube root, I get the cube root of 4, and here I get the cube root of 9. So this one is obviously going to be bigger. So this one is my maximum. So I'll even put a less than symbol in here. This one is smaller than this one. This is my maximum value. My ordered pair at 0 was 0, 0. This number is even bigger than this one, so this is for sure my global minimum. All right, what I'd like you to do is I'd like you to try this next one. Do the exact same process using this function. And I won't be totally mean here. One way to do this, to rewrite this equation, since I've got a square root on the bottom, I would rewrite this function to be 4 minus x squared to the negative 1/2 power. Now it's a little bit easier to find the derivative of. So now you can go ahead and work on that one. So here is what I found. My derivative, I did the derivative of the outside times the derivative of the inside. Derivative of the inside was negative 2x. So when I did negative 2 times negative 1/2, I get a positive x. And then this negative brings it down to the bottom. Multiply both sides by this yucky stuff on the bottom, so I get 0 equals x. That's a critical point. I also recognize that the function does not exist at positive or negative 2. In fact, it doesn't exist when x is less than negative 2 or greater than positive 2. So this one has a domain of only negative 2 to 2, but not including those. So I want to use that information to check x equals 0. So if I plug in 0 into the derivative, or sorry, left of 0, when I plug in a negative number, I get a negative divided by a positive, which is a negative. And if I plug in a number to the right of 0, I get a positive divided by a positive, which is a positive. So it went from negative to positive, so decreasing to increasing, which means I've got a min at x equals 0. I can plug this 0 back in up here, and I get 1 over the square root of 4. So my ordered pair is at 0, 1/2. There are no endpoints for this one. The domain didn't have any endpoints, so there's no other points for me to check. That means that there is no maximum. There was only one critical point. It did result in a minimum, but this one does not have a maximum.